So with all that algebra that we did to calculate average rate of change, let's get a visual for what's happening. And the visual, as I mentioned in that last video, is that our average rate of change is going to be the slope of our secant line. So let's say we have our function x squared plus 2, which is graphed over here, so it's our function x squared, but we have that vertical shift up by 2, and we want to find the average rate of change from 0 to 3. And to do that, what we saw in that last video is we don't need a visual. We could just calculate that algebraically, no problem, but then let's tie it to the graph after. So difference in outputs over difference in inputs, going to, let's do some side work here. So f of 3 is equal to 3 squared plus 2, so that's going to be an 11. F of 0 is just going to be 2. So we're taking 11 minus 2 over 3 minus 0, which is a 9 over 3. So we're getting an average rate of change of 3 out. So let's see how that comes up in our graph here. So if I have my function and I graph, we're looking from 0 to 3. So we're starting at 0 and going out to 3. What I want to do is look at the point on the function. So there I am at 0, 2, and then at 3, I'm all the way up here. And what I want to do is take a look at the line that connects those 2 points. And when I do that, what we're going to see is a nice little slope of 3. So if I take 2 points on there, what I'm going to see is I would go up 3 over 1. So across that whole line, there's a slope of 3. So on average, for our function, even though there's this curvature here, what we can do is see this rate of change from where we started to where we ended up. Now for the equation of the secant line, so this right here is giving us our slope. So what I would want to do is, let's call this y, and then I'm going to put secant down there. We have a slope of 3. And then for our y-intercept, we're going through that point 0, 2. So what we can do is just use 2. So the equation of our secant line would be a 3x plus 2 there. Let's say we look at a different interval. Let's look from -2 to +1. So I'm going f of 1 minus f of -2 over 1 minus a -2. So f of 1 is going to be a 1 plus 2 is 3. F of -2 would be a 4 plus 2, so 6. So we're going to end up with 3 minus 6 over 1 plus 2. So -3 over 3, so we're seeing a -1 out. So what I expect is when I graph the secant line, so going from -2 on our function to +1 on our function, if I connect those, I should have a nice slope of exactly -1. Which we have, a nice slope of -1 between those 2 points. And if I want the equation of the secant line, then what we would have is that slope, and then it looks like we're going through +4 on the y-axis. So my equation for the secant line will have a -1 times x plus 4. So that's how the average rate of change connects to our graph. It's just coming through as that slope of the line between those 2 points. So if we take a look at what's happening with the bee population that we were looking at in the last video, and what we could do is look at the secant line from from 1 and b of 1. So that would be this coordinate right up here. So it looks like we're at 130. And then to another point, which they're showing as here, but really it could be anywhere, where we're going to 1 plus h, and then the output at 1 plus h is the idea there. So what we could do is then, and actually h, so what it would represent is here we have 1, and then h is this increment of how far away we are. And the idea of calculus is that we want to start taking that increment closer and closer to 1. Because if we do that, as we get closer and closer to 1 on our function, we're going to start getting a closer and closer glimpse of what's happening at exactly 1. So at that coordinate that we're interested in, what is our average rate of change right at that point? So that's where we want to move the second coordinate closer and closer to get this idea. So in order to do that, if we're focused on just what's happening at 1, so it's like we're interested in finding this instantaneous rate of change, which we'll talk about even more in the next video if you're not comfortable with that terminology. And we're really focused on at t equals 1. So that would be our August with the bee population. So what we would do is look at where is that output for 1 plus whatever increment we're using minus the output at 1 over 1 plus h minus 1. And then what we could do is start simplifying that. And that would give us our slope of the secant line from 1 to some second coordinate. And what we could do is start making that secant line closer and closer to t equals 1 to start getting an idea of what's the slope that's occurring at exactly 1. And that slope that's happening at exactly 1 is what we'll talk about in the next video. So what we're going to do is start getting closer here. So I know I keep saying closer and closer, but that's the idea of calculus, is where I could then graph that secant line, but then I could go closer and then I'd get that secant line. So more and more as we get closer to t equals 1, we get an idea of, in a zoomed in sense, what is this rate of change that is just happening right here, right there for our function. And that's where we go to our next video.